All right, so far we have, in simple random sampling, we have defined the equation 3.2, which is the expected value of our sample mean is equals to the population mean, mu. We can say that if that's the case, the y bar, the sample mean, is an unbiased estimator of the population mean. So this is by definition. And then the variance of our sample mean would equals to sigma squared over n multiplied to a finite population correction factor, which is n minus n, and divided by n minus 1, 3.3 equation. If, in reality, sigma square is not known, we cannot obtain the sigma square from the previous consensus or any data available for us, we can estimate the variance of our sample mean by using our sample variance, sy squared, divided by n, and multiply to 1 minus a fraction of our sample size to the population size. Equation 3.5. Okay, so you may ask, why do we need that? We collect a sample, and then for each of the sample units, we take an average of y bar. Then we calculate the variance of y bar. What is the use of the variance of y bar? First of all, we can use the variance of y bar to assess the precisions of the estimator. So 1 point estimate y bar is not good enough to describe about the population. We can use, if you can still recall, if we take a square root of the variance of y bar, we call that the standard error of our sample mean. Using the standard error, assuming this follow a normal distribution of our sample mean, that we can construct the confidence interval of our estimator y bar. So how confident we are to say, for example, 95% confidence to say that the true mu, the true population mean, is within this range. The range would be y bar plus or minus the confidence interval. So we can use the square root of the variance to do the calculation. Secondly, for the y bar, our sample mean, we can calculate the variance of it and to compare with other estimator. So let's say we use other sampling scheme or other calculation to obtain that estimator, and also we can compute the variance of the y bar. Comparing different variances of the sample mean, the least value or the smallest value of the variance would be the best estimator of our sample. Thirdly, we can use the variance of y bar to determine the size of the sample, n, lead to n. So that could be quite interesting when we talk about number 3. But first of all, point 1 and point 2, we can use the variance of y bar to help us to assess the precision of our estimate or to compare the y bar with other estimators. If we can use equation 3.5 for the true value of the variance of y bar, given sigma square is known. But as we said, if we don't know about the population variance sigma square, we can still assess the estimated variance of y bar. Estimated variance of y bar using our sample sy squared over n and multiply to that finite population correction factor, right? Then we can still use our sample variance to estimate the variance of the sample mean. But if you can see, point 3 is a little bit tricky, because if we need to determine the size of the sample needed, then that means we have not started to conduct the sample survey. We need to determine what the sample size is, right? Then how could we have the variance of our sy squared? We'll come back to that when we come to the determination of sample size. Okay, so looking at the variance equations, if I have the variance equation with me, okay, that helps. This is the true variance of the y bar. under the finite population case. So that's equal to sigma square over n multiplied to the finite population correction factor. If sigma square is unknown, then we use the estimate of the variance of y bar. So this is the estimate of the true value of the variance. So the estimate has a head on top. This is the estimate of the variance of sample mean because we're using our sample variance as y squared for the calculation. Okay, so this factor in front for the estimated variance y bar, or this factor for the true value of the variance of y bar, we call that finite population correction factor. If we look at the infinite populations, we do not have that factor in front of it. The variance of y bar is just sigma square over n for infinite population, if you remember, right? So now we have a finite population, so we have a factor in front of the sigma square over n, and same as the estimated variance of the sample mean, we have a factor which is to be multiplied to s squared over n. What's the use of that factor? We can see that in the remarks. They are, for both of them, we call them the finite population correction factor. That should be included when we are drawing a sample from the finite population. Okay, so we can see the effect of it. First of all, let's say if the sample size, for example, if the population size is approaching to infinity, very large, so we can see that factor n over n tends to go to 0. Then the variance of y bar tends to go back to the infinite population case equals to sigma square over n. But if we increase the sample sizes n, as n increase, then we can see that, for example, if we look at the estimated variance with that factor, if n increase, if that value of n increase, the fraction of n, our sample size with respect to the population size, going to be a slightly larger number, but it is still less than 1, right? And this is going to increase, and 1 minus an increasing number, then as a result, we have a smaller factor, a smaller finite population correction factor multiplied to s squared over n. So this seems to be a diminishing effect of calculating or having a smaller value of the estimated variance of y bar. Same as the case for the true value of the variance of y bar. If n increase, and then we have a smaller numerator, n increase, a higher denominator. So as a result, the variance of y bar would also reduce, right? So if that's the case, if we increase our sample size while doing a sample survey with a finite population correction factor multiplied to the sigma square over n, it's more effective than using the infinite population case. Excuse me. As the sampling fraction increases, so if we have the sampling fraction increase, variability between samples will decrease. Then the variance of y bar will decrease, like we said. If we keep increasing the sample size when n is approaching to the population size, what happened? That becomes a census. When we conduct a census, that means only one sample could be collected. Then the variance of the sample mean would equal to 0. This is the best because no variability between the samples. Only one sample is collected. So of course, census, that's the true value we can estimate. Thirdly, the estimated variance of y bar will decreases as n increases. We just talked about that. With that increasing of that number, we can see denominator increases. So this number increases 1 minus an increasing number, and then as a result, we have a smaller factor multiplied to sy squared over n. So that gives a smaller estimate of the variance of y bar, gives a more precise estimate. When population size is large enough, then the sampling fraction becomes very small. When we do the calculation, if we look at the fraction, if our sample size divided by the population size is less than 1%, then the final population correction factor is very close to 1, then we can ignore that. We can say that the population size, whether this sampling is drawn from a finite population, is actually very similar to be collecting from an infinite population. So the variance of y bar is indeed equals to sigma squared over n. If a random sample of n is selected but with replacement, remember what we mentioned about in the previous slide, that with replacement very similar to the infinite population size, that we have the variance of y bar equals to sigma squared over n, and the estimated variance of the sample mean is equals to 1 minus 1 over n sy squared over n. This is for the case that we don't have sigma squared. So we can compare the infinite population case, the variance of y bar, or estimate the variance of y bar, to the finite case of the variance. We can see that we just mentioned. This one does not have the final population correction factor. So we can say that with the final population correction factor, the sampling scheme is more effective. And the relative efficiency is indeed the final population correction factor.